Welcome to this simple demonstration on how to perform multi-domain signal analysis of 5G base station and user equipment systems. In this video, we're going to showcase the benefits of using a mixed domain oscilloscope for analyzing RF amplifier performance. Being able to view signals across multiple domains, analyzing several different types of measurements simultaneously with a single instrument is incredibly useful in complex 5G systems where digital, analog, and RF signals interact with each other. Wireless expert Alex Krauska is now going to take us through a typical 5G system debug and validation scenario of an RF amplifier, all analyzed with a mixed signal oscilloscope. Alex?
Here in our lab setup, we have a Tektronix Series B MSO as our acquisition hardware, an AWG 70,000 arbitrary waveform generator as our source, which is producing a single NR carrier at 3.5 GHz center frequency with a bandwidth of 100 MHz. It's an uplink signal with 30 kHz SCS, 256 QAM, 11.5 dB OFDM PAPR. The AWG is adjusted for a 250 mV to 500 mV peak-to-peak signal, which is about -11 to -17 dBm composite average power. A Keithley source measurement unit is used to power the device under test. We've also added a current probe on channel 6. And on the 6 Series B MSO, we're running the SignalVu VSA software with 5GNR optional plugin, and we've configured it to analyze the signal captured by the scope on channel 1. For our device under test today, we have the GVA123 Plus from Mini Circuits, a small-scale amplifier, but it illustrates the measurement issues typical for user equipment and base station applications. We are using a ZDC-10-01203 coupler capturing the input signal on channel 1 at -10 dB down. The waveform travels out of the AWG to the DUT, where it is amplified by roughly 16 to 17 dB, then acquired by the 6 Series MSO on channel 5. We're also measuring the input signal on the AWG from channel 1. As an example, here we're looking at our amplifier that's getting good readings, starting out triggering on the RF input. And then suddenly, you see variations when we introduce a disturbance, where we're getting moments of high distortion and you wonder what's causing this. You can see that our 5G EVM is pulsing in the constellation diagram between good and bad. We can look at our power versus time, and we can see that our power drops out sometimes also. So we have all of the RF domain indications that something is wrong, and we'd like to know more about this root cause. You suspect it has something to do with the power supplies. And if you had a traditional VSA, you'd be stuck and still guessing. But with the 6 Series MSO, because it can look at both analog, digital, and RF at the same time, we can correlate the root cause. So if we look at our current probe measuring on channel 6 and RF output on channel 5, we can see that the current is dropping. So let's change our perspective to trigger on the current in the time domain rather than the RF pulse in the frequency domain. We're going to change the trigger source to the current probe on channel 6. And since we know that proper operation occurs at 47 milliamps, we'll set the trigger on 43 milliamps and we'll catch it when it's decreasing. Instead of a pulse limit, we'll set it to trigger on the current edge. We're correlating now the cause of our RF drop with the oscilloscope. And we go to SignalVu, we can now catch the moment when the current starts dropping out. Here we see that the current is perfectly correlated with the RF drop on the scope screen. Sure enough, now that we've triggered on the dropout in current, we no longer have a flickering constellation, an EVM display, and we have a much better look at our real problem. And you can see that our EVM is always high because we've triggered on the moment of failure. Now let's see if we trigger on when the current is in spec and see what happens to our RF measurements. To do so, we'll simply change our trigger direction to rising, and now we're capturing when the current is in spec. On the scope side, our RF energy level comes back as expected, and looking at SignalVu, sure enough, every capture of the 5G signal is meeting spec. So when our current is out of spec, our RF output and EVM is out of spec. Therefore, we've correlated the cause of the drop. In this demo, we are using the SMU to step current up and down. As a 5G designer, you may know more about the underlying reasons for a current change, which could be from your DPD algorithm or a coefficient loading error, which shows up as a current variation. With an oscilloscope-based solution, it's also possible to measure and calculate precise amplifier power efficiency metrics, such as power added efficiency, PAE. This device doesn't have a digital bus, but if it did, we could trigger on the digital bus and correlate problems to the digital bus activity.
Thank you, Alex. In this video, we demonstrated the basics of performing time-correlated multi-domain signal analysis of 5G base station and user equipment systems. In this case, we used an amplifier. Analyzing signals across multiple domains, analyzing several different types of measurements simultaneously with a single instrument is incredibly useful in complex 5G systems where digital, RF, and time domain signals interact with each other. The SignalVu VSA 5GNR analysis option provides comprehensive analysis capabilities in the frequency, time, and modulation domains for signals based on the 3GPP 5GNR specification. And the 6 Series MSO offers wide analysis bandwidth, high frequency coverage, multiple domains, multiple channels, and low system EVM performance. For more information on Tektronix's 5G test solutions, contact us today or visit tek.com.